Good morning everyone. So last time we did a resonance, how to identify conjugated and non-conjugated pi electron, as well as its application in aromatic, anti-aromatic and non-aromatic compounds. Today we are going to start the resonance structure, which is also called as canonical structure. So let's start. Resonance structure. This one is also called as canonical structure. Canonical structure or contributing structure. Contributing structure. So in DAT we should know these type of resonance structure. The very first one is positive charge with a double bond. Second, negative charge with a double bond. Third case, radical, single dot is called radical with a double bond. Fourth, lone pair with a double bond. Fifth, double bond with a double bond. Six, lone pair with positive charge. Clear? So these are the type of resonance structure and these are all very important one. So let's start the very first one, the positive charge with a double bond. Suppose we have this example. So first of all, you should know some basic concept of resonance structure. In resonance structure, the movement of atom is not going to happen. It's the movement of pi electron. Pi electron means positive charge, negative charge, lone pair, radical, double bond, these species, as well as vacant orbitals. So if you are going to look at this one, suppose look at here. This is not the resonance structure. Why? I told you that in resonance structure, atom movement is not going to occur. This is CH3 and here we have CH2. This is single oxygen and here we have OH. Makes sense? So here we have the shifting of atom. So this is not a resonance structure. Look at this example, suppose. So this is, you can see the number of atom and its connectivity is same in both the compounds 1 and 2. It's the movement of only pi electron, means the movement of radical, positive charge, double bond. We will discuss later how we can draw this, but you can see here this is proper resonance structure. So let's start the positive case, the very first one. This one. Look at very carefully. In resonance structure, suppose I am a positive charge. It means I am very deficient in nature. So I will grab the electron, the nearest double bonded electron. So the arrow will move like this. Look at the arrow movement. This double bond electron will move here. This bond. So simple thing is that whenever bond has electron, suppose here we have A and here we have B. So it will become A double bond B. Clear? If this is already a double bond like this and bonded arrow on the bond, so this will become triple bond. Clear? So I said that the connectivity will remain unchanged. So CH2, CH, CH2. Clear? Now look at here. This bond has a arrow, which means this single will become double. Clear? And this arrow is very important. The head of arrow indicates negative charge, tail indicates positive charge. So you can see this double bond has mid of arrow, so it means tail on this carbon. So there is a positive charge. Clear? Again listen me. We have another example, suppose this one. So I said that the double bonded electron will be here. So as a result of it, what will happen? The connectivity is not going to change. You can see this bond has arrow, so it will become double bond. The tail of arrow on this carbon, so it will be positively charged. Simple. Let's discuss few more examples. So here we have 4 examples and we are going to draw the resonance structure of this. So look at here. I said that connectivity is not going to change and the positive charge neighboring bond will grab this double bonded electron like this. So the connectivity remains same, and look at the arrow positioning. This bond has arrow, so there is a double bond, and this particular carbon has tail of arrow, so here we have a positive charge. Simple. Clear? Now look at this one. Double bonded arrow again goes here. So we will draw like this. This one has arrow, so double bond. This carbon has tail, so positive charge. Now look at the C. The double bond will be like this. Connectivity is not going to change. So you can see this bond has arrow, so double bond, and this carbon has tail, so positively charged. Clear? So A, B and C, this is in resonance, that's why we have a resonance structure. But D, this is not in resonance. You can see why? Because this conjugate species and this conjugate species are not in alternate position. You can see between them we have 2 single bond. So if any species is not in resonance, then there will be no resonance structure. So there is no resonance structure. Clear? Sometimes we have more than one resonance in a compound like this. Suppose this one. You can see this is more than one resonance. Positive single double and double single double again. So let's do one by one. In a very first case, the pi bond, the double bond will be here. So as a result of it, we can draw like this. This carbon has tail. This double bond will remain same. And in the next resonance structure, we can break this double bond to this position. And as a result of it, we can draw like this. So here we have a double bond. And here we have a positive charge. So this is the positive charge case of resonance. Now the next one is negative charge. So negative is an electron donor. So it will donate the electron to this bond and the double bond will break like this. Clear? So donor donates electron and positive is a deficient, so it will grab the electron. Again the connectivity is not going to change. CH2, CH, CH2. This bond has arrow, so double bond, and this one has a negative charge. Clear? So this is the resonance structure of this molecule. Suppose we have this one. Again look at here, negative donate and double bond break like this. So what will happen? This bond has arrow, so double bond. This carbon has hit, so negative charge. Clear? So this is the negative charge resonance structure. Let's discuss one more example, multiple resonance like this one. So in a very first case, it will donate and this bond will break like this. So as a result of it, what will happen? You can see there is a bond. Here we have a negative charge and here we have a double bond. And in the next step, again the same thing, negative donate to this bond and it will break like this. So as a result of it, it will form. Clear? So this compound has two resonance structure. Clear? More the resonance structure, suppose this is compound A and this is compound B. And my question is, which one is more stable? So it will form only one resonance structure. You can see. And the above one has two resonance structure. So more the resonance structure, more will be stability. So we can say A is more stable than B. So this is the negative charge resonance. Next is the radical resonance. Look at here, what will happen with the radical? So radical is just like a neutral one and double bond break homolytically. What is homolytically? Half curved arrow here and half here like this. Look at what does it mean. Suppose you have a double bond, a B, and if you are going to break like this homolytically, so it means A has one electron and B has one electron like this. If this one has single bond like this, so half here, so A has radical as well as B has radical. Clear? So if you are going to break this one, it will form something like the transition state in this way. So here radical and here radical. Clear? And what will happen as a result of it? Look at here. This radical combine and that will make a bond. So finally it will be like this. This radical combine, so double bond, and this will remain same. So same thing here. There is a double bond and this will be radical. Clear? We can discuss few more example. So again homolytic breaking like this. So look at here. This radical combine, there is a double bond, and here this carbon has a radical, so radical. Suppose you have this one, half here. So this bond is going to form a double bond here, and this carbon is radical here. Clear? So this is the resonance structure of a radical. Now the next one is lone pair case. I think that's fourth one. So lone pair is also electron rich species like negative charge. It will donate as well, but lone pair is a neutral one while negative charge is a charge species. So it will donate as well like this, and this pi bond breaks. Again the connectivity is not going to change. So NH2, CH, CH2. This bond has arrow, so there is a double bond. This carbon has head of arrow, so negative charge. And I said that whenever head is negative, tail is positively charged. So this lone pair, the nitrogen has tail, so there is a positive charge. Clear? Now you can ask, if you look at this example, it is going to donate and this bond is going to break. So as a result of it, it will form. You can see this one has head, so negative. This bond has arrow, so double bond. And now you can say this carbon has a tail of arrow, which means positive charge. But look at here the thing. If A has negative already and tail is like this, suppose, it means positive on a same atom and opposite charges. So positive and negative is going to cancel out. That's why this CH2 is a neutral here. Clear? But this lone pair is not a negative charge. That's why we have a positive charge because of tail of arrow. We can discuss few more examples. Suppose this one. So you can see it will donate like this and it breaks. So as a result of it, OH. This carbon has head, so negative. This bond has arrow, so double bond. Oxygen has a tail of arrow, so positive charge. And in the last session, I told you that if any atom has more than one species, then only one will be in resonance. So here we have two lone pairs, so only one. And it can be any one, so only one lone pair. Suppose this one is going to take part in resonance. So this lone pair still remains same like this. Look at this example. Look at the arrow mechanism. I said that lone pair is a donor, so lone pair donate to this bond and CO breaks like this. So as a result of it, CH3, C, double bond and H2, positive, and this O negative. Why? This bond has arrow, so double bond. This oxygen has head of arrow, so negative charge. And the lone pair has tail of arrow, so positively charged. Everything is logical in organic chemistry. Clear? Now the next case is carbon-carbon double bond. Suppose this one. So this is a symmetrical double bond. Symmetrical means you can see only carbon-carbon double bond, no heteroatom. Heteroatom means like oxygen, sulfur, nitrogen. So this is carbon-carbon double bond and we can start from any side. Look at here. Suppose this double bond goes to this carbon and then it breaks like this. So look at the arrow and tell me connectivity and number of atom is not going to change. Look at here. This carbon has head, so negative. This bond has arrow, so double. This carbon has tail, so positive. Clear? Look at here. You can start from any carbon. Suppose this one. It is going to move here, so this double bond break like this. Clear? One more thing I want to tell you. The charges will only be moved on that position which is in conjugated position. So you can see resonance starts from this point and finishes over here. So your charge must be between them. It should not be out of this carbon atom. Clear? So as a result of it, you can see this bond has arrow, so double bond. This carbon has head of arrow, so negative. This carbon has tail, so positive. Make sense? So this is carbon-carbon double bond. The benzene is very famous one. Look at this one. Let's draw one by one, or even you can draw all at once like this. It goes here, it goes here, and this here. Clear? So look at the drawing. This bond has arrow, so double bond. This bond also has arrow, so double bond. And this also has a double bond. Clear? If you are going to draw one by one, so it should be like this. This goes here and it breaks here. So draw this. So there is a double bond. Here we have a positive charge, here we have a negative charge, and here we have double. Make sense? In the next step, look at the movement. This negative donates here and this bond will break like this. Clear? So there is a double bond. And you can see this negative, this bond has arrow, so as a double bond. Make sense? But the most accurate is this one. In a single time we can draw all the resonance structure. This is the resonance structure of the benzene one. Make sense? You can see the double bonded position. Suppose this is 1, this is 2, this is 3, this is 4, 5, and this is 6. 1, 2, 3, 4, 5 and 6. So this is the alternate movement of a double bond. Suppose we have another type of atom like this one. You know, CO bond is a polar bond, so it will always break like this, in this way, always. So here as well, it means this double bond will be like this. Clear? So as a result of it, CH2, CH, CO, H. So this carbon has tail of arrow, so positive charge. This bond has arrow, so double bond. And oxygen has head of arrow, so negative charge. Clear? Look at one more example. You can see this will remain same. Here double bond, here oxygen negative, and here H, and we have a positive charge at this position. In the next step, this double bond here bond and there is a positive charge. Clear? So this is double bond of heteroatom resonance. And now the last one, the positive charge one. This one. You know, lone pair is a donor again, so it will donate to this carbon atom. And as a result of it, look at here, the bond has arrow, so double bond. Nitrogen has tail, so positive. Suppose we have this one. So it will donate like this. As a result of it, oxygen has positive, then lone pair, then H, and here we have double bond. So this is all about the resonance structure. In the next session, we are going to discuss the resonance hybrid and its stability. Clear? So in the next session, we will start. Thank you so much.